This is Rev VMware 1. So this is a custom virtual machine, which just means that we have a challenge binary, and this is going to read from a file. The file is challenge, program, and it's going to execute this, custom opcodes and do something. For our case, it's a flag checker, so it says, "Welcome to VMware 1. Please enter your password." And the idea is that you should be typing in the password or the flag, so it'll be something like this. So you can go into Ghidra and try reversing it, and this is what it looks like. This is some sort of execute function. It's just going to read from that program file and just do the different opcodes. So we can see this is opcode 1 and it's doing an addition, opcode 2 is a subtraction, opcode 3 is an and. You can go through and try reversing the entire challenge. There's another solution, and that's the solution I ended up doing, and it's instruction counting, and we're just going to brute force the flag. And so the idea is, if you were to type in, let's say, UIUCTF this is obviously not the correct character. And so what's going to happen is the challenge binary is going to compare this character, then this character, this character, this character, this character, blah, 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 until it gets to here, and it's going to exit. And this is going to execute so many CPU instructions. And so let's say it executes, 1,000 CPU instructions. Cool. If we were then to try UIUCTF bracket, because this one is the correct character, it's going to continue executing further than this one executed, and so it's going to execute more CPU instructions. So we can say maybe it's 1,001 instructions or something like that. And because of that, there are tools where we can count the number of CPU instructions. We can effectively brute force the password just character by character. So we'll try UIUCTF. We already know it's bracket, but maybe we'll start here. We'll try A, and so maybe this will be 1,001, 1,001, 1,001, 1,001. And when we get to the correct next character, I think it might be a 0. I could be wrong. Maybe this will be 1,010 instructions. And at that point, we know that this is the next character in our flag, and we'll move on to the next character, A, B, C, and continue. The tool we're going to be using for counting instructions is valgrind, specifically a tool called callgrind. And this is what the brute force script looks like. We can actually just run this real quick. So we're going to run valgrind, and we're going to run the child program. So we're going to count how many instructions it does when we give it flag.txt. Let's set up flag.txt. Let's just say we'll do this one. Cool. So this is flag.txt. Let's see how many instructions it runs. It is 157,000, or almost 158,000 instructions when we supply it this. When we supply it this, let's run it again. So 157,977. We can see it is more when we do the correct character. And that's pretty much how the script works. So like I said, it's just going to go character by character and brute force it, and we're just going to count the instructions. The rest of it's just pretty much wrapper code for doing everything. So we're going to cut out the actual number of instructions, and we're going to compare it to the last one. We're going to see if it's greater than 100. If it is, we're just going to append that flag character, and then we'll write out the flag. And we just, like I said, we're just going to brute force character by character until we get the entire flag. So we can start running it. Python 3, solve.py, and it's going to start. Sweet. So it found the first character, and the first character was an A. This script takes, I don't know, a good 10-20 minutes to run, but eventually you'll get the entire flag out. This is crypto 3-time pad. For this challenge, we're given 3 ciphertexts and 1 of the plain text, and this plain text corresponds to this ciphertext. And the challenge is hinting that they're using XOR 1-time pads, but they're reusing keys. And if you reuse a key in a 1-time pad, it completely breaks the secrecy of the encryption scheme. And so to reverse it, we're able to get the key by XORing C2 and P2, and then from there we can XOR the key with C1 and C3, and we'll get out both of those messages. So this is just an example ciphertext. This is C2, this is P2. So if we XOR those together, this is the solve script. If we XOR P2 and C2 together, we get out the key. And then from there, we just XOR the key with C1, we can print out P2, and then we XOR the key with C3, and we get the entire message. So let's run it real quick. Oh, I already have it there, but Python 3, solve.py. It says, before computers, 1-time pads were sometimes printed on flammable material so that spies could, and here's the flag, burn each key after using it. Yep. Next is crypto at home. We're given 2 download files. So we're given a chal.py and a chal.txt. So the chal.txt prints out some values. We're given E, N, and C, and the chal.py is just doing a bunch of stuff. This challenge was just a little bit strange. Basically, none of this stuff really matters. The only thing that matters is this line here and the output. And if we look at that, it's saying the ciphertext is equal to flag times E mod n. And we have n E, and C. So the only thing we're missing is flag. And what's strange too is I think this is supposed to be like an RSA sort of thing, but they're doing multiplication instead of raising it to the power. And so because of that, we can just solve this math equation for flag. We don't have to do anything special. And so that's what the solution was. So just doing some math, really we want flag. And so to get flag, we need to unmultiply it by E. And to do that, we can just take the inverse of E. So we'll do flag is equal to C. So C times E to the minus 1 N mod N. And that's it. We get the answer. So this is what the solve script looks like. We first import the 3 values, and then we do that thing I just said. So we're going to do C times POW. So we're just taking the inverse. Remember, you can't divide when you're in modulus. You need to do the inverse like this, the mod inverse. And we mod everything by n. And then from there, we just do int to bytes, because that's what they did in the challenge file, I think. Yeah, they're doing big here, int from bytes big. So we need to make sure that we also do a big endianness. We strip out some null bytes, and we get the flag. So Python 3, solve that pi. And there we go. We have RSA at home. Next is crypto group project. For this, we're given a netcat port and a download file. So let me just copy this. So this is the download file. It's going to read the flag. It's going to generate some values. So we get a generator point of 2, some random prime, 1024 bits, a random A. So this is looking like a sort of a Diffie-Hellman sort of scheme. We have the public key A, and it's just G to the A. It's going to print out some values. Then it's going to ask us for a K. It's going to do some checks. Then it's going to finish up the Diffie-Hellman, and it's going to take that shared key, and it's going to take the hash of it, and then encrypt the flag and give us the ciphertext. So there's a couple of bugs in this K check. And so K is the only input, so we know that we have to do something with K. And there's 2 different mistakes here. First off is there's these checks to make sure K is a sensible value, but they're missing a return statement here. And so it says I'm not that dumb, but then the program just keeps executing. So you could type in K equals 1. The other mistake is while K equals 1 is probably an interesting value, the K value we actually want to use is 0. And that's because if you take something to the power of 0, the result is 1. And so specifically, we want this S value. So we can imagine if we were to type in K of 0, K would go here. So B to the 0 and would be 1. So BK of 1. And then 1 to the power of A. A is an unknown. 1 to the power of anything is just a 1. And so at the end result, S is just equal to 1. And when it gets converted to bytes, we can do the same thing, and we can decrypt the ciphertext because we know what the key is. And that's what the solution was. This is it. We're just going to run the program, send it A0, so we can do that real quick. Proof of work disabled, choose a K, we choose a K of 0, and it gives us out you can see it says I set a number, but it gives us out the ciphertext, so we can copy that. Should be the same as this one. We just put it in here. We know that the S, the shared key, is just going to be 1, and so now we can execute this, Python 3, solve.py, and we should get out the flag. Yeah, it says brute force ain't so bad after all. This is Crypto Group Projection. It is the revenge challenge for group project. We're again given a download file and a netcat port. So this is the download file. It's pretty much the same, except now that they do some checks for K and they actually do the return. So we're no longer allowed to supply a K of 0, and it'll actually return this time. So cool. This time we actually have to do a little bit of crypto, but otherwise the challenge is pretty much the same. As a quick recap, our goal is to get the shared secret S, because they're going to take the hash of that and encrypt the flag. So we do need to somehow recover S, or know what S is. And our only input is we're allowed to inject this K parameter, and that'll kind of get mixed in with the Diffie-Hellman parameters. So we need to pick a clever K such that we know what S will be. Thankfully, there's a huge hint right here. They check to make sure that K is not equal to P minus 1 divided by 2. Which seems like a strange check, but if you know Fermat's little theorem, the check is not quite as strange. So Fermat's little theorem, it is POW, actually let's just do A to the P minus 1 is equal to, mod P is equal to 1. So this is Fermat's little theorem, very nifty little theorem, and using this we can kind of abuse it. Again, we're going to try to set S to be equal to 1. Being clever. And so what we have is, let me move down here. So S is equal to BK to the A mod P, and BK is equal to B to the power of a times k. So we have something like this. And we want s to equal to 1. And we also have Fermat's little theorem, if we remember it, is 1 is equal to, it can be anything, so it could be b. So b to the p minus 1 mod p. Okay, so this is what we have, and this is our little trick that we can employ. So we get to supply a k. They specifically don't allow us to do p minus 1 divided by 2 as our input into k. And that's because if we imagine a is just going to be some random number that's generated. Actually, I think it's b in this case. Doesn't matter. But whatever this random number is, if it was even, so if it was even, it's evenly divisible by 2. We're going to take a 2 out of there and multiply this by 2. And if we can split this out, so this is now b to the, basically you can split it out. And what this will happen is this will turn into a 1. And so then it's just 1 to the power of whatever a divided by 2 is. But 1 to the power of anything is just 1. And so it's 1. And so that's why they specifically check to make sure that k is not equal to p minus 1, because you can abuse this Fermat little theorem thing and get s to be equal to 1. But there's a bunch of stuff you could do. They specifically check to make sure that we don't do p minus 1 divisible or divided by 2, but we could just do divided by 3. So on the off chance that a is divisible by, or cleanly divisible by 3, we'll just take that 3 out, we'll multiply this by 3, and so when we do the power of a or b to the p minus 1, this will get turned into a 1, so this will be a 1 here, a 1 here, and so a to the power of, or 1 to the power of anything is just 1, so we just have 1, and so now s is equal to 1. It's not guaranteed that it's going to be a multiple of 3, but you know, if you try it 3 times, eventually it will be, so we're just going to brute force it. So that was the solution. This is what it looks like. We already know what the key is going to be. It's just s is going to be 1, so we just plug that in, we get the key, we get the cipher, and then we just try a couple times. So we connect to the remote port, we grab the p, we grab the k, we send back a p minus 1. Oh, I'm doing divided by 4. I think we could do 3, but I just did 4. We could check. We'll put in a 3 here. Then we grab c, the ciphertext, and then we try to decrypt it and we print it out. And then I close it and I wait 1 second, just because we need to try a couple times. So we'll do python3.solve. It's connecting. We get some ciphertext. There we go. So here was the flag. Let me cancel it. Where'd it go? Here it is. So on our second attempt, so we actually had a 1 out of 3 chance. 1, 2, and 3, and it popped out, 1 out of 3. But it says brute force worked before, but not now. So fun little challenge. This is Pwn chainmail. We're given a source code file, a download binary, and a Docker file, along with a netcat port. Cool. If we look at the C file, this is just a ret to win challenge. So we have a win function, the give flag, and it's just going to print out the flag for us. The main function is going to do some buffering. It's going to read into this name buffer 64 bytes. It's going to do an unbounded gets, so we have a buffer overflow, and then it's going to return. So, nice beginner ret to win sort of challenge. We can do checksec. Checksec file is equal to chow. We can see there's no canary, so nice and simple, and there's no pi. This is as ret to win as it gets. Basically, we're going to overflow this buffer, and we're going to put the win function on the return address for the stack. And so that way, when return gets called, instead of being returned to libc or wherever it was going to go, it's just going to return to this give flag function, and the flag should be printed out. This is what the solve script looks like. So this is just standard pwn and context setup and all that stuff. The challenge begins here. So we're going to connect to the remote host. You can do this to figure out the offset. If you haven't seen this before, you should check out my videos called CTF Cookbook, where I cover how to do this stuff. But we're going to calculate the offset, so we know specifically how many bytes we need to send until we get to the return address, and then we're going to send that. So p.sendLine, a is times offset. I'll talk about this in a second. And then we send the win address, which is just elf symbols give flag. We wrap it in p64, and we start an interactive. The reason we need this extra line, so this is just a random return statement somewhere in the binary. The reason we needed this was because of stack alignment issues. Modern libc requires the stack to be aligned, which just means that RSP needs to end in a 0. And so sometimes you just need to insert an extra return statement in there so that the stack just gets bumped up by 8 bytes. But that was pretty much it. So we can run it real quick. Python 3, solve.py, and a bunch of stuff runs, and we get the flag. Your friend, UIUCTF, you're a big shot now. This is Pwn zapping a setuid 1. This challenge was pretty crazy. I think if you're smart, this challenge was probably pretty easy. but I'm not that smart. This challenge was a very humbling experience, and I'm very excited. I really hope the challenge author releases some write-ups. I feel like this challenge is just an amazing learning opportunity. There's a lot of stuff in here that I thought I kind of knew, but turns out I don't really understand it as well as I thought. And so for that, thank you, challenge author. This was great. So the idea behind this challenge is they are exploiting something called ZApps or ZApps. I'm not really sure how to say it. And the idea with the ZApps is normally, like if I was to ship you a binary, that binary would probably depend on libc, and the binary would use the libc that is already on your system. So, if you're on Ubuntu 22 or Ubuntu 20, you're going to be using different libc versions, and the binary, just finds it and it works. And the process of finding the libc on remote systems, or any system, just, the process of finding libc, the kernel is going to invoke something called a loader. If we go, let's go here. I already have it open. If you type in ldd bin shell, we can see what bin shell depends on. And specifically, it's going to use this loader here. So this is just a known address. It's a full path address, and it's going to load libc from here. And so we can see it's using, absolute full path libraries. The idea with ZApps is, what if instead you could do local pathing? And so then you could move these entire folders around, and the binaries would just work fine because they're going to be using the local libraries instead of the system libraries. And so that's the idea behind ZApps. For the challenge author had this idea for kind of simplifying the ZApps process. And they leave a comment about setuid binaries, and that's what we're going to be exploiting. So we're exploiting a new way where in the existing ZApps way of doing things, there's like this little shim binary, and there's an extra execve call. In this way, the challenge author is able to create an exec binary that uses one less exec call by kind of doing some of the work that the kernel used to do in part of the loading process. But as part of that change, it now opens itself up to the setuid vulnerability. So I think that's the background. There's one other thing. In the challenge description, it says, oops, I left the CVE open. If we click on the CVE, basically what's happening is it's possible to abuse symlinks with setuid binaries such that you can copy a setuid binary out from a symlink, and it will retain that setuid flag. And so the setuid flag means, run as the owner, which in this case is root. So the goal of this challenge is to run as root. So and the change that the challenge author made to the binary is now, instead of using the system full path loader, they're able to use a local loader. And so it's going to look for a loader in the same directory and execute that too. So it's going to set up everything necessary for the loader and then jump into the entry point of the loader. So combining these two ideas together, it's possible to exploit it. So the idea is we can now copy a setuid binary that's currently using a loader next to it. We're going to copy that setuid binary into a different directory and supply our own loader. And then we're going to create a malicious loader such that when you jump to it, it's going to just spawn shell. And that's pretty much the challenge. So to do that, a couple different steps. First, let's connect to it, and we'll just poke around a little bit. SoCat not found. Oh, I need to be local. Okay, so we're here, LSLA. So we can see there's the ZApps folder, which is pointing to here. And what we can do is we can create actually let's just go to ZApps, cd ZApps. So this is what a ZApps folder can look like. You can do it however you want. And in here, in the build folder, is a bunch of stuff. So we have the executable binary, we have a loader, we have this library, this is a custom library, and we have libc. And we can see this exe has the special bit flag. So it's a setuid binary. And so we can just run exe. It prints out its memory map, and it prints out just a bunch of print statements, which are useful. Cool. So like I said, the first bug related to this is that we can do that symbolic link, and it'll maintain the permissions. So we'll do ZApps build exe. And so we're going to create a symbolic link to here. And if we do an LSLA and we look at exe, we can see exe still has that setuid bit set. So that means exe is going to look nearby for that loader that loader binary, but there's not one here, and so we're able to create our own and kind of inject some malicious code. So we need to create a malicious loader. This is this is the meat of the challenge. And I think for me, I ran into a lot of different hurdles when creating it, but the end process, it really wasn't too terrible. This is what I ended up creating, but there's a number of things that we needed to fix. First off, canary. For some reason, the FS register wasn't working for me, and when you do a canary, it kind of looks for that specific FS register, so I needed to make sure to disable that. I was just confused why I was getting so many seg faults at first, and so disabling canaries is one of those things. For figuring out what was crashing, thankfully GDB was installed on the remote machine, so like if we were to do, very slow, GDB exe, thankfully we're able to run it, and we can see something happened, it failed. You can set breakpoint, step over, and we can see it's not able to find the loader. So canaries was one of the issues. The other with just shellcode, just making sure the shellcode's working correctly, blah, blah, blah. When we construct our shellcode, so we're going to construct the shellcode, and eventually the program's going to jump to, like I said, our fake loader. I don't think it can include libc, because I don't think libc is loaded at this point. So we need to actually use shellcode and not just, call out, system bin shell or whatever. It needs to be shellcode. Next, because we're using BusyBox, this is a QEMU binary. BusyBox is a program that just kind of bundles a bunch of common system utilities together. And it's just like very small, very useful tool. But because of that, it needs to have argv set when you call execve. Normally when we write shellcode, we just pass null. Like if we look at syscalls, execve. Normally what we do on this argv is we just leave it empty, but technically I think it's supposed to contain the program name as the first argument. And so that way, I guess the program knows what's being called. BusyBox requires it because I think everything's a symlink to BusyBox. So when you call bin shell, you're actually calling BusyBox. So you need to have the program name as the first argument to argv. So we need shellcode that does that. We also need shellcode that keeps the permissions. So this is the shellcode I ended up finding. I had to try a bunch of them. And what's nice is it's going to do this setuid call, so that way we maintain permissions. What else? I think that's all we needed. So basically what to do, you just take this, we're going to close this, we're going to we'll call it shell.c, we'll insert that shellcode. You can see it's not importing any libraries, it's just going to call some shellcode. I had to add this attribute section text because for some reason it was going into the data section, which is non-executable, and so it wouldn't work. So once I had this, it'll read in the shellcode and then just call the shellcode. Very standard shellcode sort of stuff. The command I used for compiling it was this one. So warning all, shell C, debug, optimize for space, pipe. I found this in the make file that was as part of this challenge. I don't think it's necessary, but I just included it. No stack protector. For some reason I have that twice. I can delete that. Executable stack, just in case. My entry point is main. I'm not sure if that's necessary. Again, I was testing a lot of different things. And this is the out file as the loader. So we're going to copy that. Cool. And at this point, we should just be able to run exe. We run it, and now we have shell. And if I do who am I? A little slow, but we are root. So I think the flag was under mount, maybe. Yeah. And there we go. And now you see why it's in user lib now. All in all, very fun challenges. Definitely most of them were on the difficult side, which is good. I'm very excited to see the rest of the write-ups. Yeah, this is also my 100th video, so for any of the long-time watchers, thanks for watching, and I'll see you at the next CTF. Cheers.